Okay, welcome back. Now we're going to do a demonstration on the resistance and resistivity. The equation for resistance is R equals rho L over A. Rho is the resistivity of the material. So we have a material here that we're going to use. Mainly we're going to be doing copper. The resistivity of copper is 1.7 times 10 to the minus 8 ohm meters. And then we're going to have one wire that has a resistivity. It's a nickel silver, and it's mainly silver, but it's 18% nickel alloy mixed with the silver. Its resistivity is much higher than copper, 28.7 times 10 to the minus 8 ohm meter. And so we're going to illustrate that. And then we're also going to illustrate that the resistance depends on not only on the resistivity, but the length of the wire and the area of the wire. So if we have a wire that's twice the length, right, twice the length here, but the same area, this is twice the length, what should happen? This should have resistance that's twice the resistance of this, right? So if the resistance of this is R, the resistance of this should be 2R, twice the resistance, because the resistance is linearly proportional to the length. So that makes sense. If a wire is longer, then it's harder for electrons to traverse that wire, and the resistance of the wire should go up. This should also happen with water hoses, right? If you have a water hose of a certain length, a water hose with twice the length, it should be twice as hard for the water to go through it, and its resistance should double, right? And it also depends on the surface area, the cross-sectional surface area of the wire, right? So if we have a wire that is twice the diameter, right, than this one, twice the diameter, what should happen? If I double the diameter compared to this, let's say this one had a diameter of D, right? If I double the diameter, what should happen? The area quadruples, right? Area is proportional to diameter squared. So then the area quadruples, and if the area goes by a factor of, if the area of this we call A prime, and then the diameter of this we call D prime is equal to 2D, right? And if we square 2D, we get 4A. So that means the surface area of this one is going to be 4 times the surface area of that one, right? So what's going to happen to the resistance? The resistance, keeping all other things equal, if the resistivity and the length are the same, so the resistance is going to be rho L over 4A, right? So the resistance of this will go down by a factor of 4. I do the opposite. If I make the diameter half as much, if I make the diameter of this half as much as that, then the area is going to be proportional to 1/4 of the area of this one, right? And then the resistance of this one is going to be rho L over 1/4 A. And then the 4 goes to the top. Then we're going to have 4 times R. Then this is going to have 4 times the resistance of that. So that also makes sense, right? If I make a wire thinner, then it's going to be harder for electrons to go through that. And the resistance of that material is going to go up. And it goes up by a factor of 4 because the area goes down by a factor of 4. So let's show this now. So I have an ohm meter here. It measures resistance, and then I'm going to put it here on ohms, right? First, I'm going to measure the resistance of the wires that are connected to the ohm meter, right? 1.6, 1.7 is fluctuating. If my digital meter was more accurate, it would give me a second digit, but for now, I'm just going to approximate this as 1.6 ohms. Right, we have 10 meter wire, copper wire, and then this one is the diameter, 0.025 inches. The diameter is given in inches, 0.025 inches. It's this one, and it's wound around like this, and it's a 10 meter wire. The number 2 is this one. This one is going to be a 10 meter wire, half the diameter, 0.012 inches. So the resistance of this should be 4 times the resistance of that, right, because it's half the diameter. This one is 20 meters, so it's the same diameter as the first one, but it's twice the length. So the resistance of this should be twice the resistance of that, because it's twice the length of that one. This one is half the diameter of this one, so it should have 4 times the resistance of that one. And then this one is going to be 20 meters, 0.012. So it's going to be the same diameter as this, but twice the length of that. So this one should have 4 times the resistance of that. So here's how it should go. This one should be the least resistant. This should be 4 times the resistance of that. This one should be twice the resistance of that. And then this one should be 4 times the resistance of this one, because it's twice the length. And then this one should be 8 times the resistance of that one. Okay? And then this last one is the 10 meters long, so it goes back to the first one, same length, and 0.025. So it's the same diameter, same length as the very first one, but instead of copper, it's nickel silver alloy, so it should have a resistance that is greater than the first one by the factor of 28.7 divided by 1.7. So whatever that factor, whatever that ratio is, then that should be equal to the ratio of the resistance of this to the resistance of the first one. So let's check that one. Okay, so now I've got the wires on the very first one, and then you can see that it's fluctuating between 2.1. Okay, so I'm going to say that the resistance is 2.1 ohms, but remember the resistance of the wires was 1.6, so that's going to make the resistance of this first one 0.5 ohms. So now let's go to the second one. So I'm going to record this on the board also. So this one is 3.8. Then the next one is 2.6. 2.6. Okay, now the fourth one, which was the 20 meters, 0.012 inches, is 6.0 ohms. This is 11.2. So 6.0, 11.2. So let's write these down. Okay, so we've got the first wire 2.1 ohms, second one 3.8, third one 2.6, fourth one 6.0, fifth one 11.2. But remember the wires that I was using to test the resistance, they had an internal resistance of 1.6 ohms. So then I subtract 1.6 ohms, you get 0.5 ohm. Let's see if the pattern of the equation is working. Remember we have resistance is resistivity times length over A. So the resistance of this is 0.5. This one was a 10 meter wire. So if this one is half the diameter as that, we said it should have approximately 4 times the resistance, right? If it half the diameter, 4 times the resistance. So you can see here 0.5 times 4 gives you 2.0. So that's within our error. Remember the resistance was fluctuating a little bit, 0.1 this way or that way. So 0.5 times 4 gives you 2, and we had a reading of 2.2 ohms, so that's pretty good actually, okay? Now this one is the same diameter as this, but twice the length. 0.5 twice that should be 1.0, so that one's actually working out, right? If you're gonna have twice the length, it should be twice, and that one really works out. The last one is gonna be twice the length, and it's gonna be half the diameter of this one, right? So this one should be about 4 times more resistance than that. So you can see 4, 4.4, 1.0. Again, within the error of the instrument fluctuating this way and that way, you can see that it does work out. So this is about 4 times that, right? And then this one should be about 8 times the resistance of that, because not only is it twice the length, but it's half the diameter, which is going to be 2 times 4. So this one should be 8 times that. 0.5 times 8 gives you 4. And then this is 4.4, so it's actually pretty close. The other thing we can check, this one is the same length as that and the same diameter, but just different material. So the ratio of the resistance 9.6, right? 9.6 to resistance of this one, which is 0.5, right? So all other things being equal, the only thing different between them is the material, right? So 9.6 over 0.5, that's a ratio of what? That's 19.2. So the ratio of this to this is going to be a 19.2 ratio, right? So that should be the ratio of the resistivity of this material to the resistivity of this material, right? So 28.7 over 1.7. So you can see that it's not exactly equal to this, but again, our experiment is not meant to be perfect, but to illustrate the concept within the error allowed by the instrument, the fluctuations of the resistance allowed by the instrument. So you can see that the ratio is about 17, and then the ratio of our result was about 19. So we're not that close, but you can see that we are in the ballpark. The other thing we can do to see if this is working too is take one of these wires and apply this formula to it, the formula rho L over A, and see if we are getting a ballpark close to the answer. That's the cross-sectional area of the wire. Right? Area is pi times the radius squared. Or I can say pi times, since radius is half the diameter squared, so that's going to be what? Pi times d squared over 4. So then I could put here, right? So then the 4 goes up to the top. I have 1.7 times 10 to the minus 8. And then 4 goes up to the top, makes that 40 divided by pi. And then the diameter is 0.025 inches, so 0.025 inches. Then convert inches to centimeters and centimeters to meters, right? 1 inch is equal to 2.54 centimeters. And then 100 centimeters is 1 meter. And then I have to square that. So if I apply this equation, I should get an answer close to 0.5 ohms, right? So let's see how my answer comes out. That's actually a really, really good result, because when we measured it, we got 0.5 ohms, right? So within the fluctuations allowed by the instrument, we took the 2.1, but it was kind of fluctuating, and then the 1.6, which was also fluctuating. But then when we subtract, we still get a result 0.5, 0.54. That is actually a really, really good result. So you can do this with any of the other wires too. Take their resistivity, take their length, take their area, and then apply the formula and see how close you get. So with this experiment, we have shown the equation resistance equals resistivity times length over A. We've shown that by just changing the length, we change its resistance. We double the length, we double the resistance. If we half the diameter, we quadruple the resistance. So we've shown that relationship to hold true. And we've actually applied the equation with the resistivity and the length and the area, and we've actually gotten an answer that's actually close to the answer that we got. So with this experiment, you learn a lot, and you actually learn how to test the internal resistance of the wires of the ohm meter, and then how to test the resistance of any other wire like that, okay? Thank you very much.